Welcome all. In the last video, we have discussed the Euler's method for solving ordinary differential equations. In this video, we shall be discussing about Runge Kutta method, popularly known as RK method. There are different RK methods available. We shall be discussing two of them. One is second order RK method and the other one is fourth order RK method. In this video, we will discuss second order RK method. Okay, let's define the problem. You are given y dash, that is dy by dx, as f of xy, and the value of the function at x is equal to x0 is given as y0. We have to find out the value of the function at some other point, say xr, which is equal to some x0 plus rh. That means we wish to find out value of the function rh away from x0. Suppose we wish to find the function at say x1, which is x0 plus h. So what we do is we just integrate equation 1 from x0 to x1. Then we will get y1 equal to y0 plus integral x0 to x1 f of xy dx. Okay, this idea is explained in detail in the previous video of Euler's method. Now you will have different ideas for obtaining the value of this integral. In Euler's method, we had assumed that f of xy equals f of x0 y0. So in the case of Euler's method, we assume that f of xy is almost equal to f of x0 y0. Since f of xy is known explicitly, we can evaluate the function f of x0 y0 and we just replace f of xy with the f of x0 y0, and that then we obtained y1 equals y0 plus h into f of x0 y0. So this was our Euler's method. Okay, we just recall the idea. So how did we arrive at this formula? The idea is very simple. We assume that f of xy is almost equal to f of x0 y0 in the interval x0 to x1. So for x less than x1 and greater than x0. So in this interval, we assume that f of xy is almost equal to f of x0 y0. So this assumption leads to Euler's method. Now in the case of RK method, second order RK method, we make another assumption. So instead of assuming that the function is equal to the value of the function at the beginning, so we shall demonstrate that graphically. Basically f of xy cannot be a cannot be represented using a line, but you just guess that it is something like this for simplicity. So this is our x0 and this is our x1, and let this is f of xy, and this point is f of x0 y0. So we assume that in this interval the value of the function is f of x0 y0. So we assume that the function is something like this. So this was our assumption. Now here we make some modification. So in the case of second order RK method, we just take the average value of the function at this point, average of value of the function at this point and at this point. That means we measure the value of the function at x0 y0, then we take the value of the function at x1 y1. Then we take the average, that means we find the sum, then we divide this thing with 2. So we assume that the function is this much, f of x0 y0 plus f of x1 y1 divided by 2. So this is the assumption, correct? But there is one problem, we don't know what y1 is. Okay, so how you solve that problem? You can calculate x1 obviously, because x1 is equal to x0 plus h, no issues. But the problem is with y1. How will you calculate y1? So in order to calculate y1, we use Euler's method. So Euler's method will give you y1. So what is Euler's method? y1 equal to y0 plus h into f of x0 y0. So that's the idea. Correct. So we take the average of these function, the function values at the beginning of the interval and at the end of the interval. So this is the only change in second order Archean method in comparison with the Euler's method. Okay, then we'll get y1 equal to y0 plus h into, because we assume that this function is a constant and is equal to average of this function, correct? Then integrating this thing, you will get the constant into integral dx, that is x, from x0 to x1. So when you evaluate that, you will get h. So please note that integral dx, so this f of xy is considered as constant. Then when you integrate dx, you will get x, and you are evaluating that in the interval x0 to x1, which gives x1 minus x0, that is equal to h. So that h into f of x0 y0 plus f of x1 y1 for simplicity by 2. You can also consider this as evaluation of this integral using trapezoidal rule. Okay, why? Using trapezoidal rule, the idea is this. In trapezoidal rule, so this size is basically h. The integral is equal to area under this graph. How will you calculate the area? These are parallel sides. This side is f of x0 y0. This side is f of x0 y0. This side is f of x1 y1. Now, how will you calculate the integral? Integral equal to area of this trapezoid. Area of the trapezoid is evaluated as 1 by 2 into sum of parallel sides into perpendicular distance. So half into this half into this is the half, then h into sum of perpendicular distance into sum of parallel sides. So you can call this as also trapezoidal rule. So you can evaluate this integral using trapezoidal rule. Okay, this is alternate way of explaining the assumption. So you can either call it as trapezoidal. You can evaluate this integral using trapezoidal rule, then you will get this equation. Or you can consider that you are approximating this function by the average value of the function at the boundaries. So that's it. Okay, we have this formula y1 equal to y0 plus f of x0 y0 plus f of x0 plus h y0 plus h into f of x0 y0 by 2. So we'll write the same formula in a simple way. The idea is this: we'll have one term h into f of x0. You take h into this bracket, then there will be some h into f of x0. Okay, h into f of x0 y0. We call this as some k1. Then if you take h into the numerator, into this bracket, you will have something like this: h into f of x0 y0 plus h into plus y0 plus f of x0 plus h, comma y0 plus h into f of x0 plus, sorry, f of x0 y0. So this quantity h into f of x0 y0 can be written as k1. So y0 plus k1. Okay. So this quantity may be written as some k2. Okay. So put k1 equal to h into f of x0 and put k2 is equal to h into f of x0 plus h, then y0 plus k1. Correct? You will get y1 equal to y0 plus, this can be written as k1 and this can be written as k2. So k1 plus k2 by 2. So in general, we can write yn plus 1 equal to yn plus half k1 plus k2, where k1 is h into f of xn yn and k2 is h into f of xn plus h yn plus k1. That means suppose you are at some point, you are known at some point x and yn, you are at this point. Now you can travel from x and yn to x n plus 1 y n plus 1. That means you can evaluate value of the function at xn plus 1, that is yn plus 1, using this formula. How will you calculate yn plus 1? Yn plus 1 is given by this formula, yn plus half k1 plus k2. Now what is k1 and k2? K1 is h into f of x and yn. Since f of x, xy is known, you can calculate f of x and yn, and h is the distance from xn to xn plus 1. So this is the idea. Similarly, you can calculate k2 as h into f of xn plus h and yn plus k1. So this is the idea. This is how second order RK method is used to find out value of the function at some unknown point, say xn plus 1. Okay, let's consider one numerical example. So we must have some y dash, some f of xy. Okay, say it is some 2x. So let our function, original function y is equal to some x square plus 3. Okay, so this is not known to us. I just guessed one and I have this thing. We also know at some point, say x is equal to 0, we have y is equal to 3. So with this initial condition, we have to find out y at different x. For instance, we'll make a table for that. We are at some x. Now we have some y. So this is our starting point. So starting from this point, we will calculate k1, which is equal to h into f of x0, y0, no, or xy. Simply you can call it as f of xy. Then you can calculate k2. What is k2? It is h into f of x0 plus h and y0 plus, you need not to use 0, x plus h and y plus k1. So this will give you k2. Okay, so once you evaluate k1 and k2, you can calculate the new value of y as previous value of y plus half into k1 plus k2, and the new value of x as previous value of x plus h. Okay, this is the idea. So starting at x is equal to 0, starting at x equal to 0 and y is equal to 0, sorry, x equal to 0 and y is equal to 3, we have to travel to some point which is some, so we'll choose h is equal to some 0.1. Okay, so we have to travel up to 0.1. That means we need to evaluate the function at 0.1. So starting from 0, you must travel to 0.1. That means 0.1 away from the starting point. Okay, so we need to calculate the particular value of y. So the idea is this: we will calculate first k. Now what is our f of xy? F of xy is nothing but 2x. So k1 equal to h into, what is h? H is 0.1 into f of xy. What is f of xy? 2x. And what is our x? Present value of x is 0. So that is just 0. F of xy is 0. Because at x is equal to 0, f of xy is 0. That means our k1 is just 0. Now we need to calculate k2. So what is k2? H into, that is 0.1 into f of x plus h. What is x plus h? It's 0.1. That means the function is 2x. So 2 into 0.1. X plus h is 0.1. And y plus k1. What is y? Y is basically 3. Then 3 plus 0, that is 3 itself. But our function doesn't have any y. So it is just 2 into 0.1. Correct? So that is equal to 2 into 0.1 is 0.2. 0.2 into 0.1 is 0.02. Correct? 0.1 into 0.02 is 0.02. Now we have to calculate the new value of y. What is that? Previous value of y, that is 3 plus half into k1, that is 0, plus k2. What is our k2? K2 is 0.02. Now what is half into 0.02? It's 0.01. So 3 plus 0.01 is 3.01. So this is the idea. Okay. So we have started at 0.3 and we have traveled up to 3.01 and 0.1. So this is our new value. That means we have just replaced x with 0.1, and in the next step we will begin with x equal to 0.1 and y equal to 3.01. So with this we calculate k1. So we will get some value for k1. With that we calculate some value for k2. With that we will calculate new value of y and new value of x. Okay. So this is how the method proceeds. Okay. Now this point will come here and this point will come here. So this is how we proceed. Okay. So we iteratively do something. What are the procedure? We just calculate k1, then we calculate k2, then we calculate the new value of y, then we calculate new value of x. Okay, so these are the steps we have to do iteratively. Okay, so what is k1? H into f of xy. And what is k2? H into f of x plus h and y plus k1. What is the new value of y? Previous value of y plus half k1 plus k2. What is the new value of x? Previous value of x plus h. So we proceed like this. Okay, we begin here, we reach here, and we return to this point. So this step must be done iteratively until your required x approaches. And as in the case of Euler's method, here also as h decreases, accuracy increases. So this is an important point to be remembered. Okay. Okay, we have done only one step in the numerical example. You may try 2-3 steps again, and in the next video we shall be discussing about the algorithm and the Python code. So you can check the result obtained in the numerical example with the result obtained by the Python code. Thank you.